So my pleasure to introduce Agnieszka Zelerowicz from University of Maryland, who will talk about Lorentz gases on aperiodic tiling.
Thank you very much. Thank you for the invitation and for adjusting the schedule so that I didn't have to wake up at 3 in the morning to give a talk. Let me see if I could share the screen. Oh, I think I can. Good. All right, so I would like to talk about my joint work with Rodrigo Trevino, and we study billiards on aperiodic tiling. So before I introduce everything, like all the objects very carefully, let me just briefly say what this is about, just since I have the picture on the front page. So what we really study are billiards on the plane, just like Sinite billiards, right? So we consider we have some convex. So we imagine that we have some convex bodies all over the plane. So convex bodies. So here, those are mostly balls and ellipses, right? So those are the convex bodies on the plane, and then we have a particle that travels between them, right? So it will go in a straight line, and whenever it hits one of those convex bodies, which we will call scatterers, it has elastic collision, right? So it bounces away, bounces off of the boundary, and then changes the direction and travels the other way until it hits another scatterer, right? And the tilings, those polygonal shapes that you see, they don't really play any part in the dynamics. So whenever a particle crosses an edge of a polygon, nothing really happens. So we only use those polygonal shapes, so those tilings, they only tell us, they help us navigate where the scatterers are. So we only use tilings to define configuration of the convex bodies, but after we do it, later the tilings itself, they don't really affect the dynamics of the billiard at all. So we just have a Sinite billiard, and the tilings tell us where the scatterers are. All right, is that more or less clear, or are there any questions about that? Just the very basic thing. Okay, so there are no questions, so let me just continue with my talk. All right. Okay. All right. Physical motivation for that. Okay. So why are we using those tilings? So basically, the idea is to define the configuration of scatterers, which is not periodic, right? So classical Sinite billiard is it's a billiard which where the configuration of scatterers is periodic, and we want to drop this assumption, but at the same time, we want the configuration of scatterers to have some kind of long-range order. So we want some kind of order, but which is not periodic. And what is the motivation for that? Well, the original Lorentz gas was introduced by Lorentz as a model to study electricity. So it is supposed to mimic a movement of an electron in metal. So the convex bodies, those scatterers, they correspond to atoms of a metal, and the little particle traveling between them is supposed to mimic the behavior of an electron, right? So if an atomic structure of a metal is periodic, that would correspond to periodic configuration of scatterers, right? And this makes perfect sense. And it used to be believed that all metals have periodic atomic structure. However, later it has been discovered by Schechmann, it's a Nobel Prize discovery, that there are some metals that exhibit that have non-periodic atomic structure. However, the structure exhibits some kind of long-range order, which is non-periodic. So those, and so it's called quasi-periodic, and so those metals, those are called quasi-crystals. So quasi-crystal is everything that has non-periodic atomic structure, but it's in some sense, not far from periodic. So it has some kind of long-range order. Right? So this is where our project would lie. So, however, this is just physical motivation, but our motivation really is that this is mathematically very interesting problem to study. All right, some related results. There's not so much work done on that. So starting with the classical case, where the configuration of scatterers is periodic, those are classical Sinite billiards, and they have been studied for years by the best mathematicians in the world, and by now there is a lot known about those billiards. So let me just mention like the biggest results. So it's a Sinite billiard, because we have a configuration of scatterers which is periodic. Then we can do the simple trick, and instead of considering dynamical system defined on the entire plane, we can just restrict our attention to one period, and then we study something that is defined on a rectangle, right, on a torus. And so that everything becomes simpler, and with this representation, the billiard becomes uniformly hyperbolic diffeomorphism with singularities. So one can use the whole theory of hyperbolicity to study it. And so some things that are known, it is known that this system is Bernoulli, has exponential mixing, and satisfies central limit theorem. Those are like the biggest results. There's a lot more known. Okay, but as soon as we drop the assumption on periodicity, then we have a problem, because we cannot use the simple trick where we restrict attention to just one period. So we end up studying a dynamical system defined on a plane, and the natural measure to take is the Lebesgue measure, which is infinite. And the problem is that the whole ergodic theory pretty much fails at this point, starting with the Poincaré recurrence theorem, which we always have for when we have a finite measure. If we have a dynamical system that preserves a finite measure, then we have Poincaré recurrence theorem. So this is always a starting point to study other ergodic properties. But when we have a measure which is infinite, we don't even have Poincaré recurrence theorem. So first of all, before even trying to see if a system is ergodic or not, first question is the system recurrent? And so a person who did a lot of related works is Lenci and his collaborators. And the first result was of the type, I think, yeah, it's recurrence implies ergodicity. So the result that Lenci proved here is that if we have a Lorentz gas which is non-periodic, so we consider the system defined on the entire plane with respect to infinite Lebesgue measure, if we can prove recurrence with respect to Lebesgue measure, this implies ergodicity. However, proving recurrence, this is really the big step here. And so then later he has some works where he actually proves recurrence for some billiards, but now those are very far from what we consider. So there is one paper which is so-called quenched random Lorentz, quenched Lorentz gases. So what this is really, you can think of it as a Sinite billiard over a shift. So what happens here is you imagine that you have several Sinite billiards, so several configurations, each of them defined on a square. And then as you move from one square to another on the plane, you randomly choose the configuration of scatterers for the next square. So with this, the configuration of scatterers itself has a high complexity. And in our in our work, we consider configurations of scatterers which will have very small complexity, very low complexity, and in fact, those will be quasi-crystals. So this work is very far from ours. All right, so this is just some overview of related results, and let me just get to what we did. All right, so our idea is to use tilings to define configuration of scatterers. That way, we will have a lot more structure because tilings themselves have been studied by many people, and there's a rich theory developed on tilings themselves. And so if we borrow some of that, we can use it to study billiards if we define billiards using tilings. All right, so I will have to introduce all the basic notions related to tilings. So what is a tiling? It's a covering of R2 by compact sets, which are called tiles, such that any two tiles can only intersect along their boundaries. All right, so there are no overlaps. So really imagine like a tiling on the floor, right? So in our case, we will have a finite collection of those compact sets, which we call tiles, so finite collection of shapes. And then we use those shapes to tile the entire plane, and they will be only allowed to intersect in a certain way and only along boundaries. All right, so once we have a tiling on the plane, there is a natural dynamical system that comes with it, and this is just a translation. So once we have a tiling on a plane, what we can do to this tiling, we can choose a vector and then move all the tiles by this vector, and that way we will obtain a different tiling, right? If we keep track of where the origin is, everything will move with respect to the origin, so we will have different tiling, right? So this is a naturally defined natural dynamical system to consider once we have a tiling. Okay, and the notion that I will be using a lot is a patch of a tiling. Patch of a tiling is just a finite union, not even necessarily finite, just a union of tiles in the tiling. This is a patch. I also sometimes refer to it as pattern of a tiling, like a local pattern. Okay, and so here the basic the assumptions that we make. So we assume that the tiling is not periodic, so it's aperiodic, which means that if I move a tiling by a non-zero vector, I will obtain different tiling. This assumption, we don't actually use it in the proofs, but this is what makes our work interesting. Right? So if we had a tiling which was periodic, then this is just a periodic billiard, right? This will obtain just a Sinai billiard. So in order to make things interesting and obtain configuration of scatterers, which is non-periodic, we want to start with the tiling, which is non-periodic. Okay, so this is the first assumption. And then the second is we want repetitivity. Repetitivity is what makes our dynamical system close to being periodic. So repetitivity, so we replace the assumption on periodicity with the assumption on repetitivity. And this means that if you see any patch in a tiling, so you look anywhere on the plane and you observe a certain patch, so certain pattern, no matter what size, then you can find, then it comes with a number, like a radius r, such that if you are now at any other point on the plane, within this radius r, you will see the exact copy of the same pattern, right? So all patterns repeat. Once you see it once, you will see it infinitely often, and you will see it in a bounded distance, uniformly bounded distance from any point on the plane. Okay, so all the patterns must repeat. And then the next assumption is finite local complexity, which means that if you look at patterns of certain size, then you will always have finitely many options. Right, so there are only finitely many patches of a given size. So in order to obtain that, for example, you imagine that you have finite collection of tiles that you start with. So you have, first of all, you must have finite collection of shapes, and then you have finitely many ways to put them together, right? So for any two tiles, you will have only finitely many ways to put them together. And that with that, already that will give you finite local complexity, right? Because if you have a finite number of possibilities to put two tiles together, then it will extend to, if you take 5 tiles, you also have finitely many ways to put them together, and so on.
Sorry, a quick question. But in principle, is it possible that you'll have infinitely many different shapes in your tiling?
So we assume that we have finitely many.
Oh, okay. Okay, thank you.
Yeah. So this is our assumption. So the assumption of finite local complexity forces that there are finitely many tile types, so finitely many shapes. In principle, you could study tilings where you have infinitely many. Yes, but this would contradict the assumption of finite local complexity.
Not finitely many within a given scale, I believe. In big scales, orders might change. Do I understand it correctly? Because is it like substitutions, more sequences in the line, or in
yes, so substitution tiling would be an example of that, right? So if you increase the scale, then of course you have more options.
Yeah, but
you always have finitely many.
Yeah, so it's okay.
Yeah. All right. Okay. And the last assumption that we do is ergodicity. But in order to define ergodicity, I have to talk a little bit more about theory of tilings. So I'm just gonna put it here since I'm listing all the assumptions. There will be another assumption here, which is ergodicity, and I will explain it in a minute. All right. Okay, yeah, so here, just to give some examples of tilings so that my talk is not too abstract, because those are very concrete objects. So let me just give some examples. A big class of tilings that would satisfy all of our assumptions are substitution tilings. That's a very big class of tilings. And so here is just one example of a substitution tiling. It's a domino tiling. So for substitution tiling in general, you will have a finite collection of tile types, and then each tile comes with a substitution rule. So the substitution rule says that, like, starting with whatever tile you want, you would enlarge it by a certain scale, and then tile this bigger tile, this blown up tile, you would tile with using the smaller tiles according to the rule that is given. Right, so for the domino tilings, you have two tile types. So you have two rectangles, vertical rectangle and horizontal rectangle. Right, so really you have one tile up to rotation, but those are really different shapes, right? So we consider them as being different. And then we have substitution rule that says that if I start with a horizontal rectangle, then I would enlarge it, so I would double the size, right? So I extend, I extend all the edges by a factor of 2, and then I tile this bigger rectangle like this, right? Putting 2 vertical ones on the sides and then 2 horizontal ones in the middle. Okay, and then if I start with the vertical rectangle, I do the same thing pretty much, but just rotated by 90 degrees, right? So you see that, like, the substitution I had above is the same as the one below, just rotated by 90 degrees. But yeah, so that's the substitution rule. And then in order and that substitution rule already tells you how to get a tiling from that. So in order now to obtain a tiling from this picture, you would start with one of the tiles, so whichever one is your favorite. So let's say maybe horizontal one is nicer. So you would start with the small horizontal tile, then enlarge it and tile it according to this rule. right? And so this would be 0 step. Let me see if I can maybe do some drawings. Maybe. Okay, yeah, so this would be step 0, and this is step 1, that you have this small patch, right? And so in step 2, what you would do, you would enlarge the small patch that you obtained in the previous step. So now I would have even bigger rectangle, so double the sizes here. So now I have a bigger horizontal rectangle, and then so now all the tiles inside also became bigger. Okay. So now each tile, each shape here that I see is a tile from the previous step. Are they a big horizontal or big vertical? Right. So now I again tile this according to the rule. So I see the vertical. So I'm going to do this, and then horizontal I divide like this, and this is the same one. I divide like this, and then this I divide like this. Right. So now I have a bigger patch. And then I would keep doing this, and I would obtain bigger and bigger patches until at the limit I would obtain tiling of the entire plane. Okay, so yes, so here is a bigger picture. I don't know how many times I did the substitution here. I don't know, 1, 2, 3, 4, 5, maybe, or 6 times, and I obtain such bigger patch, right? And if you keep doing it forever, you will eventually tile the entire plane. Okay, now I have to. Okay, let me make it bigger. Okay. All right, so this was the example, like the simplest example of a tiling that one can give. It's a domino tiling. It only has 2 tile types, right? And at the end, you will have tiling that satisfies all the assumptions that we have. Another example, which is very famous, is Peneral Styling. There are many variations, many versions of Peneral Stylings. This is only one example. And this also comes from a substitution rule, but now substitution rule will be slightly more complicated, right? You already see that you have more basic tiles here, right? So you have more tile types in this picture, but it also gives a very nice picture at the end. Okay. All right. So those were just examples. And now, so tilings on its own, they are very interesting objects. They come with a natural dynamical system, which is just a translation. And many people have been studied tilings, and they continue to study them. So there is a very rich theory developed, which we are going to steal. So here is how you study tilings. There is a trick to start from one tiling and then make it into a compact metric space. And so this will be very important for us. Okay, so first of all, we consider a set of all the translations. So starting with one tiling, so we start with one tiling that we defined maybe using substitution rule, maybe in a different way. We have a tiling that satisfies all the assumptions that I listed before. And now we consider the set of all the translations of this tiling, and we define a metric on this set. So the metric will tell us the distance between 2 different tilings. And this is how we are going to measure that. So we are going to say that 2 tilings are close if we look at the pattern around the origin and it's the same on a big radius, right? So when we have 2 tilings of a plane, we look at the picture around the origin. So I look at the big ball around the origin, and if it looks the same for both tilings, then the tilings are close, right? So depending on how big is this ball. So if we have a ball of radius, say 1 over epsilon, such that two tilings agree on a ball of radius 1 over epsilon, then we will say that they are epsilon close. And up to, so okay, so I'm not being very precise. So we will also allow to maybe move the origin a little bit, but not more than epsilon vector.
Epsilon is small or big here?
Epsilon is small. So we want to say that two tilings are close, epsilon close, right? So we take some small epsilon, and we want to say, okay, what does the ball of radius epsilon look like in this metric? So I would say, okay, so I started with one tiling, so this will be the center of my ball, and what are all the other tilings that are in the ball of radius epsilon? So those are all the tilings, such that if I maybe wiggle the origin a little bit by a small vector epsilon, then I will see the same pattern.
Are you drawing something? Because we don't see.
Oh no, but maybe I should. You're right. I mean,
I thought you are drawing.
Oh no, I was just waving my hands, but you cannot see it either. That's why online talks are harder. Okay, so yeah, so let me see if I can draw. So I started with some original tiling, and then now I want to see if another tiling is close to it. So I have. Can I draw or not? Yeah. Okay. So I have a plane, right? So there is origin. And so first of all, around origin, I draw a small ball around of radius epsilon, right? So this is a small ball of radius epsilon. And so maybe another tiling I will have to move the origin a little bit. So maybe the center would be here. Okay, but now if it's here, then I draw a radius, ball of radius 1 over epsilon. So this is 1 over epsilon around this point. So not necessarily centered at the origin, but close to the origin. All right. And so I drew this ball. Okay. And so I want the pattern in this ball to look the same as the pattern around origin at the original tiling T, right? So this would be, say, T prime. So let's say this is T prime. And this ball that I drew should look exactly the same as the ball centered at the origin for the original tiling. So 1 over epsilon. Right, so for T, right? So those two should be exactly the same, right? So we have one ball for the original tiling, which is centered at the origin of radius 1 over epsilon. And then in another tiling, if I maybe have the ball centered not necessarily at the origin, but very close to origin, epsilon close to origin, I will have the ball that looks exactly like that one. Then I will say that two tilings are within distance epsilon. Right. Okay. Let me erase those. How do I? It's not a. It's not a tablet. It's just regular laptop, but I have. I can touch the screens, so it's kind of works like a tablet, but not really. All right. I don't know if I can. Okay. All right. So we have this distance. Okay, and so it defines a metric on the set of all the translations. And now what we consider is a completion of the set of all the translation with respect to this metric. Right, so we have a completion, right? So now we take all the limits of Cauchy sequences and we obtain a space, which we call the tiling space, corresponding to tiling T that we started with, right? So we started with one tiling, then we moved to the set of all the translations of this tiling, and then we extended it to a bigger space by taking completion with respect to the metric. So now we have a very big space, which consists of continuum of different tilings. And now the translations of our original tiling will form a dense set in this space. Okay, so this is a compact metric space, and it has a nice topology. Topology is generated by cylinders. I don't know if I can erase what I... Can I erase? Do I have to? Oh, okay. I'm trying to erase everything that I drew earlier because now you cannot read. All right. Okay, so now the topology is nice. It's generated by cylinders. Cylinders look like this. So first of all, we have a nice product structure on this space. The space has a structure of it's locally a product of an epsilon Euclidean ball, right? So we have epsilon ball on the plane, and then times some Cantor set. This is the structure of our space, right? So the cylinders look like that. We have a small ball of radius epsilon. So this is actually a ball which is on the plane, and so this corresponds to us allowing to move the origin a little bit, times a patch, right? So a cylinder consists of so a cylinder which corresponds to a ball in this metric would be, we have a certain patch, and I'm drawing again. So we have a certain patch which corresponds to the picture around the origin of our tiling, right? So we have a certain patch, and then we have to choose where the origin is on that patch, right? So we have a certain marking. So this is a patch, right? So that tells us what the pattern looks like. And then once we have this pattern, we choose where we want to put the origin, right? So the marking. So this will be this epsilon ball. Right, and so this gives us this product structure. So we have epsilon ball in one direction, and then we have a Cantor set in the other. Cantor set corresponds to all the tilings that have this patch near the origin. So if we put the origin somewhere in this ball, then we should have this patch around the origin. And then if we consider all the possible tilings that have that, we will obtain a Cantor set, because all the possible extensions of those patches to the whole plane, this would give us this Cantorized structure. Okay, so this is the space. Okay. Now we consider the dynamical system on the tiling space, which is R2 action. So just the translation, and then we have an invariant measure, which is defined on each cylinder in the following way. So let's remember that the cylinder, it's a patch. You can think of a cylinder as a patch times an epsilon ball. So we assign to a cylinder like this a measure, which is the frequency of a patch times just the Lebesgue measure of this ball. Okay, and how do we compute the frequency of a patch? Well, when we are on a tiling, we can just count how many copies of a given patch we see, right, within a ball of certain radius, and then divide by the volume of this ball, right? So we have the frequency of a patch, which we measure once we fix a tiling. So we fix one tiling, then we can compute the frequency of a given patch on this particular tiling. Right, so this is how we compute it, and then that would give us a measure which is actually invariant under the R2 action.
Excuse me, a question. Yeah. Does this limit always exist under your assumptions on the tiling?
That is a very good question. And under my assumptions, the limit exists, yes. Another question that one could ask is, does this limit depend on the tiling, right? Because we have now the entire tiling space, which is composed out of continuum of different tilings, and now one could ask if a frequency of a patch depends on the tiling in the space. And so in general, it may. So this would be a little bit problematic for us. In general, you can cook up an example of a weird tiling space on which this frequency would be different, would depend on the tiling. Okay, and so this is where my other assumption, where I used my other assumption that I said that I would explain later. This is where I use the assumption of ergodicity. So ergodicity in this case would mean that that the frequency does not depend on the tiling, or we would consider just one component in which the frequency does not depend on the tiling. So for example, if we have, okay, so maybe this is getting a little bit complicated. So for example, if we just stick to the class of substitution tilings, so the ones that come from substitution rules that I mentioned before. So for all every tiling that comes from substitution tiling is uniquely ergodic. This is a result by Solomiak. So in this particular case, if you have a tiling which is obtained from substitution rule, no matter what substitution rule, but you have a tiling and you know that it came from a substitution rule, then it will be uniquely ergodic, which means that when you extend to the tiling space, it will not affect frequencies of patches, right? So even when you extend and not only look at translations of your original tiling, but actually move to a tiling space, it will not affect frequencies. The frequencies will be the same for every tiling in your tiling space. And this is the same as to say that your tiling is uniquely ergodic. But we don't actually need our tiling to be uniquely ergodic. So what we say is, okay, let's just assume that we have a tiling which is ergodic. So if it happens to be some weird tiling space, when maybe we have two ergodic components, so maybe we can divide our space in two components which have two different frequencies. So we would just take one, right? So this is just us trying to be a little bit more general and say, like, we don't necessarily need to consider only substitution tilings, or we don't necessarily only need to consider tilings which are uniquely ergodic, but we just focus our attention on ergodic component, right? So bottom line is that our measure will look like this. We'll have a frequency of a patch times Lebesgue measure, right, on cylinders. Okay. Any questions at this point? No more questions. Okay. Okay, so we have this measure. Okay, so now this is all we really needed to know about tilings to continue with our work. And now what we want to do, we want to use the structure of a tiling to actually define Lorentz gas. So what we are going to do, we are going to define now Lorentz gas on a plane, but we are going to use a tiling. So let's say I started with some tiling T. Perhaps it was a tiling obtained from a simple substitution rule, maybe some other tiling, okay? But I now want to define a configuration of scatterers S, which will align with patterns of this tiling, right? So I want the collection of scatterers. So I define scatterers on the plane, but in such a way that they are pattern equivariant, which means that if I have two different points on the plane, maybe very far, but when I look on the tiling, I see the same exact pattern of a tiling in those two places. Then I should also see the same scatterers in those two places. Okay, so this is what we want to do. And our other assumption is that the billiards that we consider, they should be of category A. It means we want a finite horizon. Finite horizon means that there is a uniformly bounded time between two collisions. And we assume no corners. No corners means that if we have two scatterers, any two scatterers will not overlap and will not touch, right? So they are actually separated. And since we assume that that the configuration of scatterers must agree with the patterns of a tiling, and our tiling has finite local complexity, which means that no matter how big a patch I consider, I only have finitely many options for this patch. It also means that I have finitely many local configurations of scatterers. And that would also mean that the time between any two collisions is actually bounded away from 0. Right, so I cannot have scatterers which are uniform, which are arbitrarily close together, because I only have finitely many options for local configurations of scatterers, and I assume that there are no corners. So that means that any two scatterers actually are separated. Okay, so we have this, and so once we are able to define a configuration of scatterers which only depends on the pattern of the patterns of the tiling, then in fact I can lift it to the entire tiling space, right? Because now I know when I'm in another tiling in the tiling space, but this tiling has the same patterns, right? Has the same patches as the original tiling. So once I have patches, I know how to put scatterers in them, right? So I can lift the whole billiard from the plane to the entire tiling space. And so this is what we call the collision space. And this is, and then we consider a billiard on this space. Okay, so this map F is defined a collision on the collision space. What this really is, it's at this point, it's a continuum of different billiards, right? So each billiard is defined on a plane, but has different configuration of scatters, because configuration of scatters depends on the tiling, right? So for every tiling, we have different configuration of scatters. Okay, so at the moment, we have this weird billiard, which is really composed out of continuum of different billiards. And so this is our map, right? And we this is it. Okay. Example of how we can define such a billiard. It's very easy to do when we have a tiling which is a substitution tiling, because then it is enough to define configuration of scatterers on each tile, just on every tile type, right? So we have finitely many tile types. We define configuration of scatterers on each tile type. We just have to be a little bit careful so that we don't get something weird on the intersection when we put two tiles together, right? So here I did for the domino tiling, I put in the corners, I put like quarters of a ball, so that no matter how I put two tiles together, I will always get a ball, right, at the intersections, right? And then in the middle, I can put whatever I want. So, right, so those gray tiles, them not tiles, those gray shapes, I put them in such a way that when I put two tiles together, they will always form a ball, right? And then in the middle, I put for the horizontal tile, I put two scatterer types. So one is, I think, blue and orange, right? And then for the horizontal one, I put different scatterers, different shapes, right? So I have green and red. And now I can extend this to the whole tiling, right? Because I see whenever I see the horizontal tile, I put scatterers like this, and when I see vertical tile, I know how to put scatterers inside of it as well, and that gives me this configuration here. Okay. All right. What do we know about this tiling? What about those billiards? Okay, so they are going to, so now we have something interesting happening, is that now those billiards, they will inherit properties both from tilings and from the original Sinai billiards. So in a leafwise direction, when I'm on one single tiling, So each tiling is invariant under the dynamics, right? Because I never go from one tiling to another, right? So leaf-wise, on a single tiling, we have all the properties of Sinai billiards. We have behavior very similar to Sinai billiards. But then we have this transverse direction, which tells us like what happens when we look at the tilings, which are the same cylinder. And that gives us something else, right? So when we put everything together, we, for example, immediately get a measure which is invariant under this billiard. And this measure looks like this. This is the measure. So let me say a little bit. Okay, so first of all, it makes sense to parameterize our scatterers. And so instead of, so when I have a scatter, so for every scatterer type, so let's say I have one scatterer type, which is some kind of shape, like convex shape like this. I can parameterize it, and I can Pat, do you have a question? Okay. Oh, someone is making noise. Okay. All right. So, okay. So points in our space, they look like this. We have a point on the boundary of a scatterer and a direction in which it's going to go, right? So a direction, because we are on the plane, it will be an angle between negative pi over 2 and pi over 2. Right, so I can actually represent it as a rectangle where I put the angle here on the vertical axis. So I have pi over 2, negative pi over 2, right? So this is really the angle theta. And then the horizontal line will correspond to the arc length rho. Oh no, in this picture it's actually r, but I think later I'm using rho. So let's say r. Okay. So when we use this parameter, so r is the arc length and theta is the angle. And when we use this representation, then leaf-wise, when we are on a single tiling, then the following, the measure that will be preserved is cosine theta d theta dr. So leaf-wise, so when we are in the direction of one tiling, when we are on one tiling, then we have this measure which is preserved cosine theta d theta dr. This is the measure that is preserved under the dynamics leaf-wise if we didn't see this other direction. And this is exactly the measure that is preserved for Sinai billiards. This would be it, right? So the Sinai billiard is just defined on a rectangle, so we don't have this other direction. And then the measure which is preserved under the billiard is cosine theta d theta dr. But we have much bigger space, so we have also this transverse direction, which corresponds to different tilings that would have maybe the same scatterer, but at the origin, but look different away from the scatterer. Right, so we have this transverse direction. So the transverse direction tells us what is the local pattern around this scatterer, and this is this measure d nu, which is the frequency of a patch. So the measure d nu is a frequency of a patch. So we have the measure, and so this is the measure which is invariant under our dynamics on tiling. On our billiard defined on the tiling space, the collision space. Okay, so this is the measure. So the measure has a nice product structure, right? Like leaf-wise, we have cosine theta d theta dr, and in the transverse direction, we have frequency of a patch. What happened here? Just trying to change this. Okay. Okay, so I think I wanted to elaborate a little bit more on hyperbolic properties of this. Okay, so yeah, so let me just, so here is a short list of properties, and now I will go to the long list. So maybe, so okay, so we have a measure which is invariant under the dynamics, and the measure has this nice product structure, and it's given by frequency of a patch times something which is absolutely continuous with respect to Lebesgue measure. And then I will elaborate on this in a second. The system itself resembles a partially hyperbolic system. And the reason is that in the leafwise direction, we really have hyperbolic properties. But then there's this transverse direction, which we want to think of as the central direction. Okay, and yeah, which may exhibit very slow linear contraction or expansion. So this is just the short list of properties, and now I want to give you a long list of properties and elaborate a little bit more. Okay, so yeah, so really we think about this system as a partially hyperbolic system, and this is why. When we look leafwise, when we are just on one billiard, on one tiling, then we see hyperbolic properties. And most properties that have been established for periodic billiards, for Sinai billiards, they have their leafwise versions in our case. And this includes this long list of hyperbolic properties, which are very strong. So all the technical lemmas regarding length and regularity of stable and unstable homogeneous manifolds, they translate to our case. Results concerning the regularity of the holonomy map, but only leafwise holonomy if we are within one tiling, not transverse holonomy. But so leafwise the holonomy map is regular. Growth lemmas, and the most important result, which is the fundamental theorem of the theory of dispersing billiards, that tells us, helps us measure the lengths of homogeneous manifolds. All those results, they automatically, the proofs automatically hold in our case if we only restrict ourselves to just a leafwise direction. And here is the reason.
So I think it is so-called fundamental Sinai lemma, that if you have small, short unstable manifold, then they become denser and denser. Right?
Yeah.
Fill almost everything. Okay.
Yes. So this is a result of Sinai, and it's called the fundamental theory of dispersing billiards.
Mm-hmm.
I didn't state it. Maybe it was a good idea to state it because it's really like the central result that we also use. But yeah, it really tells us that, like, if the measure of smaller, like the measure of shorter ones decays, so we have a lot of long ones. Like very exact estimate. So anyway, so here is the reason why all those results, the arguments automatically follow in our case, is because all the estimates that are done for Sinai billiards, they involve several things. They use several things. They use uniform bounds on the curvature of a scatterer, and uniform lower and upper bounds between collisions. So those are really the two ingredients that you need in order to obtain all those results, right? So Sinai billiards, they don't really for those results, they don't really use periodicity. They just use those things. They use that we have uniform bounds on the curvature, lower and upper, and uniform bounds on the time between collisions, also lower and upper. If we have those things, if we have those components, then all the results follows. And in our case, we do have that. And this follows from finite local complexity. Because when we have finite local complexity, that means we have finitely many scatterer types, which means that we must have uniform bounds on the curvature. And we have also another thing that follows from finite local complexity is that we have finitely many possible local configurations of scatterers, which means that we have uniform lower and upper bounds on the time between collisions. I mean, uniform upper bound for the time between collisions follows from finite horizon, which is something that we also assumed, that we have finite horizon. Okay, and so once we have that, then we have stable and unstable cones. And in those cones, we see uniform contraction and expansion, respectively, right? And then we can build the rest. Then we can obtain all the other results from that. Okay, so this is what happens leafwise. If we restrict our attention to just a single tiling, this is what we see. But now here is the difference. So the slide says hyperbolic structure, but this is also really about partially hyperbolic structure. So for Sinai billiards, let's see how we obtain unstable manifolds, for example, or like how we study Sinai billiards in general. We have finitely many scatterers, and so for Sinai billiards, we can represent each scatterer as a rectangle, right? So this is the picture that I already sketched earlier, that every scatterer I can really represent as a rectangle, such that the vertical direction corresponds to the angle theta, right? And then the horizontal direction is the arc length, is of the boundary of the scatterer. So for the Sinai billiard, we have finitely many scatterers, so really we can represent our space as a finite union of rectangles like this, right? In our case, it's different because we are in a tiling space. So now for us, every scatterer type comes with a cantorized union of all the tilings that have this scatterer in the center, right? So our space is a union on finitely many products of this type, a scatterer type times this cantorized direction, this transverse direction that corresponds to all the tilings that have this particular scatterer in the center. Okay, so this is our space. So for us, we have continuum different rectangles, right? So for us, every scatterer I can parameterize by this rectangle. But then when I go ahead and try to do analysis, so one thing that we do, we look at singularity curves. The singularity curves will look different on different tilings, right? Even if we have the same scatterer type, but when we are on different tilings, our singularity curves will look different. And so I wanted to talk a little bit about that. So what are the singularity curves? So singularity curves correspond to grazing collisions, right? So when a point will have a tangential collision with the boundaries, right? So this is when the angle is either pi over 2 or negative pi over 2, right? So we start, so at S0, those are really just the two horizontal lines, right? So this would be S0, those two horizontal lines. The first one is the angle pi over 2, the second angle negative pi over 2.
Excuse me, may I ask a question? So I wonder, just to clarify, so the choice of horizontal here is arbitrary, right? But instead of choosing minus pi over 2, you can choose another range, say from minus pi over 6 to 5 pi over 6, right?
No, it is angle with vertical between minus pi 2 is reflection.
Yeah, so I want the pi over 2 to correspond to grazing collision. So okay, so
oh,
here's,
I see.
So,
okay.
So when we have, for example, a ball, like the zero angle is the one that is sticking out, right? So the one that is just an extension of a radius, this would be zero, angle 0. And then this is pi over, no, this is negative pi over 2, and this is pi over 2, right? So the two angles, pi over 2 and negative pi over 2, they correspond to tangential collisions. So those are the bad points. Those are our singularities. Okay, and so yeah, so S0 is just points which are already tangent to the boundaries, and now we can push those far backward and forward to find points that will eventually be tangential, right? So when we push those points backward, we will obtain stable curves, which are those decreasing curves. So in the rectangles, you see there are curves that actually look like decreasing, right? They go down. Those are stable curves. And then we have unstable curves, which are symmetric about the axis theta equals 0. And those are unstable curves, which are increasing. So those I obtained by pushing forward singularity curves under the dynamics. Okay, and why are those important? Because actually the unstable curves, they will accumulate on unstable manifolds. So eventually they will give us unstable manifolds. So when we have now now the stable and unstable curves, they divide our space into chambers. And so, for example, for every n, I can look at the connected component of this rectangle minus s minus n, so all the unstable curves up to negative n, and I look at the chamber that contains my point, and then in the limit, it will actually give me an unstable manifold. Right, so the unstable curves, they actually accumulate on unstable manifolds. So this is how we can later study stable and unstable manifolds and their lengths. And so here's what I'm trying to show is that if we take now two tilings which are, say, relatively close together, so I have those two copies of the same scatterer that are kind of thicker, right? So let's say that those are relatively close together, which means that for some patch of relatively big size, the two tilings have the same pattern, right? So on a ball of certain radius, they look the same, which means that if I push forward the singularity curves on both of them, then up to some point, I will get the same images, right? Pushing the singularity curves backward and forward up to some point, I will get the same picture because the dynamics is exactly the same if I have the same local pattern. And so here, this is what my picture is trying to show, is that, for example, here, the singularity curves S1 and S2 look the same for those two tilings, right? But then I go to S3, so S negative 3, and now I see that they are maybe different because by pushing the singularity curves like 3 times under the dynamics, maybe I already am in the area where the patterns of the tiling look different now. So right, so I left the ball of where the tilings had the same patterns, and now I'm in the area, in the region where they have different patterns, and so they have different configuration of scatterers. So the images of singularity curves will also look different. And so at the end, no matter how close the two tilings are, they will have different stable and unstable manifolds, right? So this is very problematic because this means that there is no central holonomy. As I said, when I said earlier that our system resembles partially hyperbolic system, this is how we want to think about it, but at the same time, there is no well-defined central holonomy that would push unstable manifolds of one to unstable manifolds of another, because, and this is exactly why, because they, up to a certain point, we know that singularity curves look the same if we have tilings which are the same, but then eventually they will always be different, and this is where we obtain where we have problems. Okay. All right. So this is this hyperbolic structure, right? So we have, but anyway, we always have this hyperbolic. So we always have those unstable manifolds at each on each level. It's just that they look different for in different tilings. And now I wanted to, I think, mention a little bit about how distances change in the transverse direction, because there is a reason that we want to think of the transverse direction as a central direction. So now I imagine that I take 2 points which are copies of each other. So maybe 1 point in this tiling, and then there is another point in that tiling, right, which is a copy of that one. And let's say that we push those 2 points under the dynamics and how the distances between the 2 points change. And so this is this. So the distances between 2 points, they change really slowly. And so this is what I don't want to draw anymore. Okay, so this is how the distances change between 2 points. So the point of this slide is to show that they change really slowly. So let's say that we have 2 points which are very close to each other in the tiling space, but they're on different tilings, right? So which means that they are really close in the transverse, but in a transverse direction. So let's say the distance between them is 1 over r, which means that they are in 2 different tilings, that you can think of them that they are both origins of 2 different tilings, and those 2 tilings overlap on a big ball of radius r. Okay, so this is the picture that I draw. So for x, I draw a ball of radius r, and I know that when I go to y is on a different tiling, but the ball of radius r around x looks the same as the ball of radius r around y. And okay, by finite horizon, we also know that x in k steps cannot move more than k times m, right? Where m is finite number, so we have finite horizon. So we have control of how far a point can travel away from itself. And now let's say that k is much smaller than r. So we know that since the ball of radius r looks the same for x and y, this means that those points will travel parallel to each other as long as they are in this ball, right? Once they leave this ball of radius r, then maybe the configurations of scatterers will be different and the points will diverge. But as long as they are in the same ball, the picture looks the same. The dynamics is exactly the same, right? So the points x and y will travel parallel to each other as long as they are within this ball of radius r. And so this is how the distances cannot change too much, because say I pushed point x under the dynamics k steps. So from x it went to fk of x, but it couldn't go really far, not more than k times m steps, right? So now I can see what ball of what radius I can fit in around fk of x, such that I'm still within this original ball of radius r. And so the radius now maybe is smaller, but so this would be some r prime, but it cannot be less than r minus km, right? So now the distance between fk of x and fky is less than 1 over r minus km, right? Where the original distance was 1 over r. So the distances, they cannot change fast, right? So they can the points either can go can separate really slowly, or they can also get together really slowly, right? So we could also be moving the other way, and maybe from a bigger ball to a smaller, from a smaller ball to a bigger ball, and then the points would be get closer, but also it cannot happen fast. All right. Okay, so that was it. And now the main result that we obtain. So the main result that we obtain for this tiling is K property. So under the assumptions that I listed, the map has K property with respect to this measure, which was the product measure. And then there is some consequence of that result. Yeah, I thought I would have enough time to talk about the proof of the K property, but I actually spent like it took me a lot longer than I thought. So I would probably won't be able to talk about the proof of the K property, but I can talk about consequences of K property. Okay, so all right, so we have K property for the system, which was defined on the collision space, which is really continuum of billiards. So now what I want to do is I want to go back to the original setup, which was just a billiard defined on a plane, right? So really what we were interested in is just one billiard, which was defined on the plane. And so now we want to go back to this original billiard and see if we can say something about it. So it turns out that K property will give us mixing for functions which are pattern equivariant. So we have, which means that if I have a function on the plane, whose values agree with patterns of a tiling, right? So in this case, this would mean that if I have two different points on the plane, but the patterns of the tiling look the same at those 2 points, then also the value of the function should be the same, right? So we consider functions which are pattern equivariant, and those are closely related to functions defined on tiling space, so-called transversally locally constant, which also really is the same thing. It just means that they are constant on patterns. And then there is a relation between them. Should probably go just a little bit faster. So here is the relation between, so when we have a function which is pattern equivariant, we can study the planar average of this function, right? So there's a function defined on the plane, and we study the planar average, which is like we integrate this function over bigger ball of bigger and bigger radius and divide by the volume of the ball. So this is the quantity that we study. And for every pattern equivariant function, there is a function defined on the tiling space, which is transversally locally constant, function h. And turns out that this planar average of the function g is the same as the integral of the function h with respect to this measure, which was invariant for the billiard. Okay, so we have this relation. And now this relation will tell us, okay, so because we know that we have K property on the tiling space, so in particular we have mixing for transversally locally constant functions. And so this will tell us something about pattern equivariant functions. So we have now this result. If we have two functions now on the plane, which are pattern equivariant, then we have this mixing result for planar averages. Okay. And so this was it. And then we have another result, which is ergodicity. But so this is like a Birkhoff ergodic theorem. But again, I want to emphasize so that this only holds for functions which are pattern equivariant. So this will, the rest is proof of the K property, which I would just skip probably. So what I wanted to emphasize is that, okay, so we have those results and we can relate them. So we have the K property, which is a rather strong property for the billiard, which was defined on the collision space. So it's kind of an odd dynamical system, which is really composed out of continuum different billiards. And now we want to go back and say something about the original billiard, and we can, but we have to be very careful. So we have those results that they look like mixing results, and this is like a Birkhoff ergodic theorem, but it only holds for a certain type of functions. So it only holds for functions which are pattern equivariant. So the value of the function should only depend on the local pattern of a tiling. So in this sense, we have ergodicity. However, if we ask, like in the classical definition, we don't have that. We don't even know still if the billiard, if we have recurrence for the original billiard, right? So if I want to ask if the original billiard, which was defined on the plane, is recurrent with respect to Lebesgue measure, I don't know the answer yet. Right, so we don't know if we have recurrence, so we don't know if we have ergodicity in this classical, in the classical sense. However, if I only restrict my attention to pattern equivariant functions, in this sense, I do have ergodicity. I even have mixing, right? So what it means? So we have recurrence in the sense that we have recurrence to a pattern, right? So if I'm only interested in a pattern but not location on the plane, that yes, I do have recurrence. I will come arbitrarily, infinitely many times. I will visit every pattern. Okay, but if I'm asking about particular point on the plane, I don't know if I have recurrence there. So this is a little bit strange, but this is what we had. Okay, I wanted to talk about proof of K property a little bit, but I will not be able to. So I just want to finish by saying what we want to do next. So the main next thing is Bernoulli property. We would like to know if the billiard that we define has Bernoulli property, and this turns out to be much harder than we thought it would be. And at this point, I don't even have intuition if it is Bernoulli or not. I'm starting to think that it may not be. But this is the main next thing that we are working on now. We would like to be able to say something about rates of mixing. I think they are slow. And the question is, can we say something about if there is a central limit theorem? So any results that were known for Sinai billiards, like to what extent do they translate to our billiards? So so far we have K property. We don't even have Bernoulli at the moment, and the question is, what other, like how similar are they to Sinai billiards, or how different are they from Sinai billiards? So those would be interesting to find out. All right, and so I think this is everything I had to say, and thank you very much.
Thank you.
Thank you very much.
So,
Any questions?
May I ask a question?
sure.
Is there any other example from the billiard world of a system that was shown to be K but not Bernoulli?
From the billiard world, I'm not sure I understand. Like Sinai billiards, they are known to be Bernoulli, like the periodic
Exactly.
case.
No, that's why I'm asking, because
Yeah.
If there is a precedent, you said that you believe, your intuition is that it's K but not Bernoulli. So I'm asking if there is such a known example.
I mean, not necessarily from billiard, but so the thing is the following. So here's the thing. If we study Sinai billiards, so uniformly hyperbolic ones, I mean, yeah, so Sinai billiard periodic one, it's a uniformly hyperbolic system with singularities. And it is known to be Bernoulli. but our system, the way we define it, it becomes more partially hyperbolic system. And so I don't know if there are any, I don't think there are known examples in billiard world, but in general, I think all examples, most examples that are known of systems that are K are not, but not Bernoulli, they actually are partially hyperbolic. So this is what makes me think that we may be in this regime.
Mm-hmm.
Yeah, so the partial hyperbolicity is what may cause a system to be K by not Bernoulli.
Let me say something.
Mhm.
Let me say something. So that not partially hyperbolic, but just classical Sinai systems are Bernoulli. This is part of Pearson, what I call Pearson Sinai theory, in fact.
Mhm.
That if you have ergodicity, then you have K and you have Bernoulli.
Yeah.
If these singularities behave well, and I took part in writing such a book where main authors are Katok and Streltsyn
Mhm.
many years ago. This is just Pearson theory of singularities.
Yeah.
So that's indeed, if partially hyperbolic, then might be something new, but if it is classical, then ergodicity already and non-zero Lyapunov exponents already imply K and even Bernoulli.
Yes.
This system looks to me a bit similar to this Kalikov example of system which is K but not Bernoulli.
Kalikov?
Yes,
Oh,
the
that's
one with
TT-1.
all shift on in 2 dimensions. That in 1 dimension we are always having hyperbolic behavior, but there is kind of other dimension which tells us which hyperbolic behavior we are applying.
Yeah.
And this is somehow on some level of intuition similar, that each little part, each little scatterer is hyperbolic, but we have some kind of drift, so we are choosing different and different. The choice of scatterers is another dynamical system, and altogether the system could be somehow similar.
Yeah, I will have. Yeah, I will have, thank you for this. I will have to look, because yeah, I mean, this is right now. I think I'm on a search for examples when it is known to be K but not Bernoulli, and just looking how one can go about proving that, because I think this is where I'm really leaning. And another thing that that makes it hard to prove Bernoulli, and that what also makes me think that it may not be Bernoulli, is that this is something I haven't written yet, but I think maybe I will write a paper soon, is that we have very low mixing rates. Like, even though we have K property, but if you try to estimate mixing rates, you can actually see that they are very small. Because on one hand, so mixing means that you can move from one pattern to another and it will mix. But when you are actually on the tiling and you want to travel from one pattern to another, like they will be very, very far from each other. And so it will take a long time to get from one to another, and that will make the mixing rates very, very low.
Yeah. Yeah, I was wondering about this mixing rate, because yeah, it wouldn't fit in the usual machineries very well if you want to prove something positive somehow. At least from what I know about machineries to prove the K correlation. I mean, the old ones of Sinai and Chernoff may be more suitable, which I don't know so well, but. I don't know. It seems very hard to at least to prove some decay. For me, it looks that way, at least, but I don't.
Yeah.
I didn't think about it at all, of course. but it's of course interesting if you, but you think it's fairly slow, really.
Yeah, I think I can find the upper bound for the rates of mixing. So yeah, I can say that they are slower than. Yeah, so maybe this is something I should type. At first I thought, because when we started working on that, our mindset was that, okay, like when we do this and use the tiling spaces and Sinai theory, we can combine the two and just get all the same results as for Sinai billiards. So we had, like when we started, we thought, okay, so first we are proving Bernoulli, then decay of correlation, everything will be great. But then we quickly realized that we proved K, and then we hit the wall. I think we wanted to do coupling, and then we realized, wait, there is no way to couple those things because they're just, yeah, the mixing is just like not fast enough. And yeah, but our mindset was still like into trying to prove positive results. But now I'm starting to realize that maybe I should start proving negative results. Maybe this will be easier for that system.
Yeah, K is the Sinai fundamental lemma. Just the thinner strip, the less is in singular lines. So, or in the limit, almost everything is filled by one set in the partition.
Yeah.
But Bernoulli in this Katok and Jean-Marie Strelzin, it was extremely difficult. In piecing theory, to prove Bernoulli is extremely difficult. So this is very difficult word.
Yeah. Yeah, already for Sinai billiards, but
yeah, already for Sinai.
Yeah.
I remember Jean-Marie fighting with this for 2 years, maybe, to understand piecing. And piecing also had very big difficulties to do it precisely in his PhD paper 50 years ago.
Yeah. Yeah. So anyway, if you have like any suggestions, like even later on, like please don't be shy to email me, because I will really appreciate like all the suggestions that I can take.
Let me say one more thing, that many years ago I worked in so-called linked twist mappings. So you have a family of pairwise disjoint horizontal annuli, and you take first mapping as twists in each of them, and a family of disjoint vertical strips or annuli and twists in each of them, strong, so that one circle bounding the strip is not moved, and the other circle is rotated by multiplicity of 2 pi. And then the situation is like for billiards. You have, if you compose both twists, you obtain hyperbolic, but with plenty of singular lines. So it is something that is easy to draw, unlike billiards, which is sometimes difficult to draw these two coordinates, angle and the place. So I worked with this. I have even a paper about 50 years ago, no, maybe 40 years ago, in an Annales called Normal Superior. But somehow I didn't understand the Sinai fundamental lemma at that time. So I had stronger conditions, assumptions for twists that we get K, I think, not only ergodicity. Or maybe, I don't remember precisely, but in fact, this fundamental lemma worked for everything. I didn't know this.
So you proved K, or what is the result for that?
Finally, I proved everything, but to prove K, I needed to assume more in this paper.
Okay, so you also
but it was because I didn't know this Sinai fundamental lemma, which worked in that case. If I knew that, which, by the way, people were telling me, Wojtkowski taught me many things in that time, I would do it in a simpler way. But somehow, So anyhow, I just wanted to say there is another object which is maybe simpler than billiards, where
Yeah.
the same phenomena happen.
What is this called? Like, how can I?
Linked twist mappings.
Linked?
Linked, zaczepione skręcenia.
Oh, linked.
Linked twist mappings.
Twist mappings.
Yes, so I meant, yeah, so I have preprint from about 1980 in Yashes, big preprint, and parts of this were published. Main part in Analytical Normal Superior.
I see. So you say that this may be easier to study than the.
Yes, yeah, because you can draw everything.
I see.
These coordinates and billiards are a little bit abstract. You are in higher dimension.
Right. I see. Yeah, it may be worth looking into as well.
Yeah.
Any other questions or comments?
No, very nice. We should maybe make a seminar, small seminar to prove the Sinai fundamental lemma. It is a fantastic thing. It's beautiful. And do you know that the same scheme is Lasota-York, existence of absolutely continuous invariant measure? When you have space of functions with bounded variation, if you iterate forward, then the jump in density, because of non-continuity, it shrinks. There are new jumps, they shrink when you iterate, etc., etc. It reminds cutting of long horizontal narrow and long horizontal cylinders, cutting by singularity lines. There is some similarity.
Yeah.
Which similarity I was taught, in fact, by Lysan Yang many years ago. She understood this.
Yeah, well, this appears somehow. I mean, it's a question of expansion versus cutting or folding.
Yeah, maybe. I had a manuscript that time by her.
Yeah, but this appears sort of also in this on stuff, and it appeared for Lysang in connection with the billiards. It's the question of how the expansions wins over the cutting.
The title is cutting versus expansion, yes?
Yeah, well, it's very informal. It's not written anywhere, but it's all over the place.
So. It made on me very big impression.
Yeah, but no, but this is somehow. I mean, also say for Henon, it's sort of a folding courses, very small segments, but they're also expanded. And expansion allows, say, what Collison and I told these escape situations when images are very long, and in spite of cutting, the expansion wins somehow.
Because cutting is transversal to expansion, so you don't lose much, less and less if your rectangle is very long and narrow.
Yes. So this is somehow a game played.
Okay, great. So, Artyom, we finish?
Yes.
More questions? Agnieszka, thank you very much. It was very,
thank you again for inviting me.
Very interesting.
Thank you.